Hi friends, welcome to the channel. Today's topic is study of BPSK transmitter receiver using suitable hardware, setup or a kit. So this topic is related to digital communication laboratory playlist, and this video will cover the BPSK transmitter receiver theory and this experiment, whatever the study of BPSK transmitter receiver using suitable hardware or a kit is divided into three parts. Today's topic is theoretical part, and the next video will be of how shall we do the connection for the same. Okay, and after that already I shared you one video which is related to how to see the waveforms and the spectrum of a BPSK signal. So coming to today's topic, like it is a theoretical concept for BPSK. Okay, so we will try to understand how exactly the BPSK waveforms looks like, what will be the modulator block diagram, what will be the demodulation block diagram and its related explanation, and a concept called carrier reconstruction. Okay, so this carrier reconstruction circuit is something a new concept, because you people are may be aware about what exactly PSK is and what are all the different modulation demodulation techniques are. Okay, but now before I go to the concept of what is BPSK, I feel we had a certain detailed discussion with respect to what are all the different digital modulation schemes like ASK, FSK, right? After that we have seen PSK in the previous digital communication playlist theory part. Okay, now what we will be doing today, so we will concentrate directly on what is binary phase shift keying. Okay, so actually BPSK is a phase modulation technique wherein my input is a digital data, okay, digital signal. Okay, so other than that input, what are all required for the modulation purpose? No doubt input signal, which is modulating signal, and a carrier, right? So we will start with that. So now we see the BPSK modulator block diagrams look like this. We are already aware that for a particular modulation we need one input signal, okay, and one carrier signal. So here also for BPSK it is same, only the difference is my input signal is of digital in nature. Okay, that digital only you can say like binary. Okay, so that's not the reason binary sequence or a binary signal is given as an input as a modulating signal, and another one input will be a carrier signal for the balanced modulator. It's simply a product modulator. Don't worry about anything like what exactly balanced modulator, I did not remember all those things. You leave all those things. It's very simple. It is a product modulator. Its task is to perform a product between both the incoming signal. Okay, now it is a binary or a digital signal, and this is a carrier signal. Already we know that always usually we prefer a carrier signal is of very high frequency compared to that of message signal. That concept we people are aware, because that is a mandatory concept related to modulation process, right? Now this input is of digital, right? Okay, carrier is of analog, right? So how exactly my output signal look like? Okay, for the BPSK signal my output signal look like this. Now the question is how can I get such signal? Okay, how can I get such signal? That is a very important question actually. So now we will see how can we get such phase shifted signal. So here you can observe, this is my input signal, right? The first one is my input signal, right? And I have a carrier signal also, right? I have a carrier signal too, right? So but the question arises, how am I getting like this? How my modulated signal is looking like this? Okay, you can observe that like whenever there is a transition from 1 to 0, 0 to 1, so there will be a 180-degree phase shift is happening here. Okay, so you may ask like only why 180-degree only. Don't worry, my input signal will have only two possibility, logic 0 and logic 1. Okay, if my input signal has more than two possibility like 0 0 0 1 1 0 1, at that time the phase shift will be different. Now the question arises like why 180-degree? For two possibilities out of available 360-degree, 360-degree divided by 2 will give me 180-degree phase shift. Why 2 divided by 2? Why I am doing divided by 2? Because it is a binary PSK. Means two possibilities, two different signals like logic 1 and logic 2 I would like to represent by using BPSK modulation scheme. So that's what 360 divided by 2 will give me 180-degree. How can you say this as a 180-degree? It's very simple. A signal is wishing to go like this, but it is completely inverted. So actually this signal is going like this, right? But because of 180-degree phase shift, this is completely inverted. That's what I used to say. This is a 180-degree phase shift. Okay, so that's the reason. Now the question arises, how shall I be able to get such signal? Okay, so already I stated in the previous slide like if I will be doing a multiplication among these two signals. Is it true? So yes, it is true. Now here we will enjoy the concept of what exactly what different type of line coding schemes I will be using to do such things. Okay, let us observe. I wish to go for polar NRZ. What happens? Okay, how do you represent logic 1 by using polar NRZ and logic 0 by using polar NRZ? You're supposed to recall that. That's what I said, like what are all the takeaways from the PCS. That video link I'll be sharing in the description box, so you can go through that. Okay, so that's what. See here, logic 1 I wish to represent by using plus 5 volt or plus amplitude, right? And 0 volt will be represented by minus amplitude in case of polar NRZ. So that's what I wish to take. You see here I am representing logic 1 by plus 5 volt and logic 0 by minus 5 volt. So now you do one thing. If you have a confusion like plus 5 minus 5, it will be a typical and all. So you take plus 1 volt minus 1 volt, no issue. Okay, you multiply. So 1 volt, let us consider 1 volt only. Okay, let us consider 1 voltage. 1 volt multiplied by this part. Okay, this is continuously varying, right? But this is constant like 1. So this is continuously varying. This you consider it as a x multiplied by this positive voltage will be my normal x only. You see there is no change in any signal from here to here, because up to here my signal is 1 plus 1 volt only you consider. Okay, this plus 1 volt multiplied by this x will give me x only. Now for the logic 0 it is minus 1 volt or minus 5 volt. Minus 5 multiplied by x is my minus x. You can observe the signal is going up, but the signal is going down. So that's what this, if it is a x multiplied by minus 1 will give me minus x. You can observe here, right? Means it is an inverted version of this carrier. From here to here, whatever the carrier is there, no, its inverted version is this one. Okay, so after this, once again there is a transition from 0 to 1. This is my original signal, right? 0 to 1 transition means once again I will be multiplying 1 volt with this x will give me x only. So I am getting x. Okay, this is the way how exactly BPSK signal is looks like and how exactly it is coming. Okay, on using polar NRZ concept and carrier multiplication I am getting a BPSK signal. Okay, if you have any doubt, you please comment in the comment box, so I'll be replying there. Don't worry. Okay, shall we proceed? I feel we can proceed here right now. Okay, now what do you think with respect to demodulation process? So in the demodulation, which signal we will be getting first? Which signal we will be getting first? We will be getting this as a input signal for the demodulation. Yes, true, this is true. Okay, Next, my question, like how shall we bring this incoming modulated wave to be demodulated into a original binary or a digital signal. So this is my expectation, right? From this signal I supposed to get this signal, correct? Because you can see in the previous slide we have transmitted this only, right? We have transmitted digital data, right? So that's what, from the modulated signal my wish is to get digital data. Now the question arises, how shall I get it? It's a simply a reverse process. It's simply a reverse process what we have done in the previous case. Okay, what exactly reverse process I supposed to consider? No doubt I'll be comparing a modulated signal with a carrier. If they are in phase, I'll get a logic 1. If they are in out of phase, I will get a 0. Let us observe that. Okay, now you compare it. Is this signal up to here, are they same? Up to here I supposed to take. Okay, up to here, whether these two signals are same? Yes. If it is same, logic 1. Okay, from here to here I'll be comparing with carrier. Now they are out of phase. Out of phase implies logic 0. Okay, so whenever the modulated signal and the carrier are in phase, I'll be getting a logic 1, or I will be detecting it as a logic 1. Or else if they are in out of phase, modulated signal and carrier signal, then I'll be getting a, or I will be detecting it as a logic 0. Okay, so I feel you are comfortable with this right now. So if anything goes wrong or anything you would like to ask, please comment, no issue. Okay, so now now we will think like how shall we make a demodulator. Okay, so you can observe here, to the demodulator I will be having modulated signal and I need one carrier signal so that I'll be able to get a demodulated wave, right? So this is what exactly required for the demodulation. So that's what I wish to go for, a demodulator diagram in this way. See here. So what exactly it is showing me? This is a BP modulator to which a modulating signal is coming, and I'll be comparing this modulating signal with a carrier signal. Okay, if I do that, then resultant wave will be a modulated wave. Sorry, here it is like modulated signal it is written, but what is the major reason I tell you? Actually this modulated signal is to be connected here. Okay, I wish to split this BPSK signal demodulator into two parts. Let us see how. Let us see. Yes, I'll be getting one carrier reconstruction block. To that also we are supplying our modulated signal. Okay, and there will be next block to which I'll be having a BPSK demodulator. Means the same diagram I'm splitting it into two parts because you should know, you should understand the practical point of view. That's what I'm doing this. Okay, so demodulator you can write this much in the theory, no issue. Okay, for the practical purpose also, in theory also, if you would like to grab good marks and all, so all those things, whatever it is, for your more clear understanding, so we will be having a carrier reconstruction block separately and BPSK demodulator, or you can say directly this as a product modulator. Once again, no issue, because a carrier is coming from here and one modulated wave is coming from here. Here you can write like a product modulator, no issue. This you keep like BPSK demodulation, and in here, one second, this you can keep like a BPSK demodulator. Here you can use like product modulator because it is doing a product between these two. So now you see here carrier reconstruction, what exactly it is. So I'll be discussing this in very detail, don't worry, in the next slide. So here a product modulator or a BPSK demodulator, what it will do, it will take a modulated wave and same modulated wave is fed to here also. Okay, what exactly carrier reconstruction is doing? On taking modulated wave, it is generating a carrier and feeding it to demodulator. Okay, after this you will be getting a demodulated wave like this. Okay, so this is a process from the modulated signal, which modulated BPSK modulated signal, I'll be supplying the same signal to carrier reconstruction block also, and even BPSK demodulator block also, or a phase modulator, phase demodulation also you can say. Okay, so here you may ask one question like, sir, why carrier reconstruction is required? It's very simple. In the previous slide you have seen modulated signal in comparison with carrier signal, you got a original message signal, right? So that's what. So modulated signal I wish to compare with a carrier signal. So that's what, from the modulated signal I wish to generate a carrier signal. Okay, after doing comparison between these two, currently available modulated signal and the carrier signal, I will be able to get a demodulated wave. Okay, so if you want, so you can go back and you can see once again the previous slide. Okay, so now I wish to go for how exactly this block, like second part, is exactly looking. So all the different components present, components are not like blocks present in the demodulation and carrier reconstruction block. Okay, so that's fine. Now we will see what exactly it is happening here. So this is B of t, which is our original bit stream, and this is cos omega naught t, so it will be a carrier. Bit stream multiplied by carrier will give you a modulated wave, and you can observe here bt into cos 2 omega naught t, so this will be my modulated wave. Okay, this is the equation for your BPSK modulated wave. So sometimes like you supposed to write such things also. Okay, so BPSK modulated wave form, what will be the mathematical expression? So this is the mathematical expression for BPSK modulated wave. Okay, this will be sent to two blocks. One is carrier reconstruction circuitry, so this complete is my carrier reconstruction circuitry, and this lower one you can say, like I said na, phase demodulator or a synchronous demodulator. So this lower one is my demodulation stage. So this upper one is carrier reconstruction stage and lower one is demodulation stage. You can observe like the same signal same BPSK modulated signal is fed to both the blocks. So in the carrier reconstruction block there are three sub blocks are there. Example: square law device, band pass filter, and frequency divider network. Okay, no doubt, if the square law device is used, this signal, whatever the signal is coming, that signal will get square. Okay, now I'll be thinking of only generating carrier frequency. That's what I'm only dealing with, cos square. I'm not dealing with any amplitude here. Okay, cos square omega naught t plus theta. So why square is coming? Because it is a square law device. You may ask like, what are all the different square law devices are there? No doubt, all the non-linear devices or a semiconductor devices are acting like a square law device, so you can easily use them like BJTs and all. Okay, so after this your expression looks like this. Okay, next, band pass filter. So after squaring you may get a different frequencies, like cos square theta you can be splitted into cos 2 theta, right? Okay, so only cos 2 theta plus something, right? So but you want only cos related signal, so that's what you are filtering out rest of the things by using band pass filter. Okay, cos square omega naught t cos square theta is equal to what? 1 by 2 times of cos 2 theta, right? So that 1 plus cos 2 theta. So that expression only. So you don't want lower frequencies, that's what you are applying it to band pass filter, so you will be getting a cos 2 times of omega naught t. But what is my interest? My interest is to get only cos omega t, right? Cos omega naught t. I don't wish to have cos 2 omega naught t, because I supposed to get a original carrier here in comparison with modulated signal. So that's what. So cos omega naught t plus theta I wish to get. That's what I am doing. Cos 2 omega naught I am applying it to frequency divider by 2. So if I divide my frequency by 2, what happens to this? This 2 will go, so that cos omega t will remain. So that's what cos omega t will remain, and this cos omega t I am using it for the demo purpose. Okay, so I am using the same cos omega naught t for the demodulation purpose. From here what exactly it is coming? It is a modulated signal. You can observe here square root of 2 ps into bt cos omega naught t plus theta. This is coming here, and here what it is exactly coming? Cos omega naught t only. Okay, you can observe here after completing this operation, okay, comparison operation between current modulated signal and the recovered carrier signal. If I do the product modulation, what exactly I am getting? Bt square root of 2 ps into cos square omega naught t plus theta. So you can observe it is like looking like once again a modulated signal multiplied by cos theta. Yes, cos square theta, that's fine. But what can you write for a cos square theta? It is 1 by 2 times of 1 plus cos 2 theta, right? Cos square theta, cos square omega naught t can be written like 1 by 2 times of 1 plus cos 2 theta, right? So that's what exactly. After this I'll be applying it to an integrator. Okay, actually integrator is a low pass filter. Okay, so this cos square theta is splitted into, or it can be break down into 1 by 2 times of 1 plus cos 2 theta, right? So that cos 2 theta I don't want, because I am not interested in carrier at the demodulation stage, right? After demodulation I wish to reduce that carrier concept. So that's what 1 plus cos 2 theta whatever it is there now, that cos 2 theta I am avoiding. I wish to take only 1 multiplied by 1 by 2. So it will become, you can observe here, it will become b of t in the square root ps divided by 2 into tb. Why tb is coming? It's very simple. Integration of a constant go to t. That's what tb is coming. Okay. Now question arises, why square root of 2 is coming down or in the denominator? It's very simple. 1 by 2 plus cos omega 1 by 2 times of cos 2 omega naught t, right? That 1 by 2 times of cos omega naught 2 is going out. Only 1 by 2 is left. So that 1 by 2 multiplied by this much is supplied to an integrator. We will get a tb times of 1 by 2 times of input. So that's what bt in the square root of ps divided by 2 means. Actually after splitting this equation you will be getting divided by 2, right? So that's what square root of ps divided by square root of 2, that will be equal to square root of ps by 2. Okay, so in this way you can observe here what is there at the finally, what you are getting finally here, you are getting bt only, but certain amplified or attenuated factor, right? bt along with some amplified factor. So that target is what I am actually sending. I am sending bt after modulation, right? And my final output should be, I supposed to once again get bt, but some amount of attenuation or amplification is happening. Okay, so this is how exactly I am recovering back my original message signal. So this is what our today's topic. Actually I covered the theory aspect of BPSK transmitter and receiver. Okay, in the next video we will see like how to do the connections for the practical experiment. Okay, and also the waveforms also. Okay, the waveform related video already I shared, but what are all the where and all we supposed to observe the waveform is very important. So that's what in the next upcoming video we will see how to see the BPSK waveforms on doing connection over the kit. Okay, so that will be our next incoming video. So please keep watching. So I wish thank you for your patience listening. So we will have a next video in next upcoming topic. Okay, thank you.